Hello everyone. Today in this session we are going to discuss about Neo4j as a graph database to power logistic problems. Okay, to solve logistic problems. So I would like to know, does anybody know like vehicle routing problem in logistic? Does anybody know? Okay, that's cool. Okay, so you're familiar with it. But if nobody knows, let me explain what exactly is vehicle routing problem. It's like uh, travel salesman problem. Okay, when we are learning programming, so there's a concept like there's a one salesman and he has to traverse through the graph. Okay, in order to reach one specific point and turn back. Okay, so what's the shortest path? So vehicle routing problem is the same problem but on major scale, where we have multiple constraints like time constraint and different customers, different stops. Okay, so what vehicle routing does is that it tries to find a shortest and the optimized path to solve this problem. Okay, so basically what happens is that in logistic companies, okay, or even any delivery company, these vehicle routing problems are not one-time fix. It's not static. It's continuously happening to X number of interval, like every 5 minutes, not 5 minutes, 5 seconds or something like that, because the rider is keep changing the location, the new order is keep coming. Okay, so the system has to be very optimized and very efficient in order to give the rider a quick result. So that's where exactly the graph database, specifically Neo4j, comes. So basically, instead of having a traditional tabular database, okay, why we use graph database in the first place? So let's suppose there's a scenario where we say that we need to retrieve all the couriers within the 10 minutes of reach within the neighbor. Okay, so if we use traditional relationship database, so what happens is that we have to use multiple joins. Okay, and these joins are very computationally costly, because they do cross computation and then filter it. Whereas in the graph database, there's no such thing. Okay, there's no cross computation. It's just simple traversing. Okay, so that's why it's more optimal, okay, to use graph database. So as I said, that the data is already in the graphical representation, so it's already easy to traverse. Like for example, the node is courier, order, restaurant, and the edges are row segmentation and time window. If I have like enough time, I can show a small demo. Nah, okay. Anyways, apologies, it's not working. Okay, in this Neo4j database specifically, we have a syntax called cipher. Okay, so now what is difference between traditional SQL query and the cipher query is that it is more easy to read, okay, because it has less complexity, less joining syntax. So like for example, right now, if you can see, right now, as you read the query, you can easily read that it's trying to fetch all the couriers available in that zone, okay, and all the orders that are pending in that zone, and find the shortest part in that exactly, okay, with a level of 6 deep. Okay, like for example, right now you see from 1 to 6. That means that the adjacency nodes has to be maximum 6, because there is a possibility of going in cycle, or it can go to n level deep. So we have to limit that. So basically, in the whole system, how exactly are we using it? So let's suppose in the Uber Eats, for example, okay. So what happens is that the rider is constantly getting updates. How? So behind the scene, what happens is that the rider emits the GPS location to the system, to the main system. So main system, what does? It filter out the data, okay, the graph data using Cypher based on the current location, the surrounding, the shortest path of shops, and the customer. There are different loss of constraint. Then what happens? Then the actual main thing happens is that this data is then converted back into tabular form, and then it is send it to MIP resolver. Okay, so what MIP resolver does is that it's an optimization tool. There are lots of different optimization tools like Google OR, Groby, and there are other. So what they do, they do the combination computation, okay, combinatorial computation to find all the best possibility and filter out the best in that best possibility. Okay, sorry, we'll have a Q&A later. So okay, so once that best possibility is retrieved, then it's sent back to the rider. Okay, so why specifically Neo4j in that situation? In the other graphical database, okay, there are two types of database, graphical database. There's native and non-native. Okay, what's the difference? In non-native, the data is stored in traditional manner. For example, in ArangoDB, it is saved in document database, in JSON document, and then it is mapped as a graph in memory. Okay, it serves different purpose. Okay, but it is slow in our scenario. Okay, and that where the Neo4j is like get on the top. So it is like a native graph, and it has index-free adjacency. So it doesn't have index. Okay, so whatever the DML operation you perform, it instantly update where the current node is. Okay, and on top of that, they have large community. So even if like tech people, okay, the technology is good if the community is larger, because you get the solution, okay, which you're already trying to solve. There is already library for that. So this data science library and the large community, that's where the Neo4j tops. Okay, speaking of again, the same thing I'll repeat, because the data science library built in the Neo4j application database, so we already have some built-in functionalities like shortest path, where the digestra algorithm is already built in within the query, so you don't have to manually add or type. There's a community detection where it automatically creates a cluster based on the data and the nature of data. Okay, and there's a centrality. That means that it also detects the bottleneck, okay, between roads and maps. So there are lots of different tricks and techniques built in the Neo4j, where you don't have to implement manually. Okay, again, last but not least, the whole thing, okay, the graph database is used in logistic as to eliminate the NP hard problem, because all these MIP resolvers, they are good, but the problem is that the city is big, very big, okay, and you don't need to fill all the data to that MIP resolver. So you need to cut down to the minimal data set. Okay, so that's where the graph database comes. So yeah, this is overall the presentation.
How do you keep the location data updated on the graph? Because for bikes or weighted bikes, like Google Maps used to have, you need to keep it very fresh, like event traffic data.
See, that comes down to the data architecture, how the data is modeled, okay, and how the query is optimized. And it all comes down to you have to, execute the query.
The graph or is somewhere else?
No. See, you're the rider. Okay, so you have the phone. So the actual GPS location is coming from your phone. You ping to the system. System takes that location and ping it to the graph. So yeah, that comes because this Neo4j graph is optimized because I said it's native. Okay, it saves the data in the point as a pointer. Okay, not in any other format. So it returns the data much faster as compared to other graph data or other relationships. So it happens in like microsecond. So yeah.
What does MIP stand for? And can you explain?
MIP stands for mixed integer programming. Okay, it's basically a solver. Okay, it is basically used in all this vehicle routing problem like Wolt, Uber Eats, Uber. Okay, so you order your food. Okay, so how does system knows that there is a rider nearby? Okay, who can deliver in the fixed limited 30 minutes time span? Okay, because whenever you order, the maximum time limit is 30. How is it possible? Okay, how do they do that? There are thousands of riders roaming around the city. Okay, so does he have the capacity or is he fully occupied? Does he have the full fuel? So there are lots of constraints. Okay, so calculating manually will be computationally very costly because that's an NP-hard problem. To overcome that, these systems use already defined resolvers. Okay, they are called MIP resolvers, mixed integer programming resolvers. So what they do, we give them the data set with these constraints, okay, and they give the best optimal result. And in short, like, you know, knapsack problem. Okay, it's a knapsack problem, but in very complex way. Thank you.